lower RPM doesn't necessarily mean better fuel mileage. You're driving something and you're on a nice flat road, nice and easy, low RPM. It starts to incline. All of a sudden, the car or truck downshifts. Then it may have to downshift again. Now you're having to do throttle input to get the car to keep going at the same speed. You are defeating the purpose of having a lower numerical gear with having a lot more throttle input, which affects your gas mileage. For a long time, the theory was lower gear ratio, higher RPMs, worse mileage. I think what people did was put a lower gear in for that tire diameter or quarter mile you want to hit or anything you want to hit. You've got torque and horsepower instant now. And I think people use the accelerator more because it's there, which can draw the mileage down.
As much power as you have on demand, if you use that power, you're going to use fuel. So, if you have a more optimally higher numeric gear, you're going to have more power. If you utilize that power, you're going to end up consuming more fuel because there's a certain amount of power it takes to get something up and going. A lot of times the factories will put out vehicles undergeared with numerically lower gear so that when it goes into the government standard and the government theoretical output, they'll show higher mile per gallon with a higher gear ratio, but it's not real world testing that they do on there. It's all theoreticals. Ultimately, if the vehicle manufacturers go with those standards, then they put out vehicles that are dramatically undergeared.
Within gas engine applications, there's a huge misconception that a lower gear ratio, so installing a numerically higher labeled gear set, translates into more engine RPM, which equates to more fuel consumption and reduced miles per gallon. If lower RPM used less fuel, something like a 1-to-1 rear gear ratio would dramatically increase fuel mileage and would be a super popular option. But it's not.
Because a 1-to-1 gear ratio, you wouldn't even be able to drive the vehicle. The engine speed you'd end up with would be so low that you couldn't get it rolling and it wouldn't maintain its speed going down the road. That's why you don't see a 1-to-1 or even a 2-to-1. You used to see low 2s before overdrives. Generally, when there was lower numeric ratios than they currently are running in some applications, now it was for cruising. You'd find them in a lot of Cadillacs and big car applications that all that they were worried about was having low engine speeds for the comfort, less vibration. Put your foot onto the throttle, it would accelerate very smoothly.
The best example we can think of to help explain gear ratios simplistically is a lever. Imagine a seesaw, perfectly balanced. By pressing down on one side, the other side will rise with an equal force. In this case, we expend 1 kilogram of pressure to lift a 1 kilogram weight. When we put their values into the equation, this yields a mechanical advantage of 1, which isn't actually an advantage at all. So what if we wanted a mechanical advantage of 2? Since this first lever is a 1-to-1 ratio, the fulcrum is equidistant the workloads, and both sides are displaced the same distance during a work cycle. For a mechanical advantage of 2, or a 2-to-1 ratio, the input lever arm needs to be doubled in length. Now, in order to lift the 1 kilogram weight to the same height as before, let's say it was 2.5 meters, the input lever has to travel twice the distance. That might not sound beneficial, but it is, because having a mechanical advantage of 2 means that only half, 50% of the original force is needed to do the same work. A 3-to-1 ratio would mean the input lever is displaced 7.5 meters to raise the weight, but only requires 1/3 or 33% of the original force. 390, an actual gear ratio, simply means 390 to 1. It would require about 25.5% of the original force necessary. 410 to 1 ratio requires 24%. The difference between these last two ratios may not seem like a lot, but how this actually translates through a drivetrain can result in significant power differences. Let's go back to the seesaw. Though we are forcing the input side down, the weight is not raised straight vertically, but displaced at a curve. The rotational equivalent of linear force is torque. But what does that mean? Let's pretend I push this pipe from the left side of the screen to the right. What is the direction of the force now acting on the pipe? Is it forward, since that's the direction of the originating push? Or what about this way, since that's the direction of the roll? Both are right. The force is all directions away from the pipe due to centrifugal force. So where does that leave torque? Torque is the magnitude of the force applied, like how mechanical advantage is the magnitude of the linear force. When it comes to a vehicle, the reciprocal motion of the pistons gets turned into rotational motion through the drive shaft. The drive line meshing at the pinion and ring gear changes the direction of the rotational motion, twisting the rear axle shafts, which in turn rotate the wheels. If you want to think about it in terms of a lever again, the gear ratio is the mechanical advantage. The drive line, where pinion and ring gear meet, would be the input force, and the gears driving the axle shafts would be the output force. Let's look at leverage and torque side by side. For leverage, the longer the input lever, the further the input force has to travel. Likewise, for torque, the numerically larger gear number will take longer to travel through rotation than a stock gear, but in doing so, requires a smaller fraction of the power to maintain speed once optimal RPM is achieved.
When you're under geared, the thing that you notice is seat of the pants is you just have an absolute lack of power. The engine has plenty of power, but if you don't have it reduced and run through the transaxle into where you can propel, you lose power. People refer to that as loading up the engine, where you're pushing the engine, running a lot of throttle, which will actually generate a lot of heat that's contained within the engine. It's part of power. Heat is energy. And anytime that you're losing energy that isn't being directly put down to the ground, you're losing efficiency. Everything in there, just the whole driveline is being taxed more with not having the proper amount of gear reduction. A lot of times if you're generating that amount of heat, the engine's not operating in its optimal RPM range. That's where you lose mileage, especially on acceleration, even trying to hold speed on the freeways. You're trying to punch through air. Yeah, and it's just not fun to drive.
Nope.
When a vehicle's properly geared, it allows the engine to stretch its legs. So it allows the engine to operate in a RPM band that it's more efficient in. Generally you're going to use less throttle input. So even though your engine speed may be higher, your foot's less in the gas at the same given speed with the same given acceleration. So it's going to be an offset for acceleration and efficiency. But once you get to where you're going and you get up to that speed, you're barely in the throttle at all compared to having a under-geared application where you're just like pushing that motor to keep the vehicle going and punch through the air.
What a ratio change numerically higher does is help that engine torque propel that vehicle through that drag.
With an optimal gear, your engine's going to run cooler overall. The fluid, whatever, I'm not a scientist, so I don't know. The fluid movement in the torque converter is not losing as much energy through heat being dissipated. More of that energy is literally making it to the rear end and pushing the vehicle. Putting in testing over the last year, we've done several different applications of what a lot of people would consider as overgearing. In every single case, they've maintained their fuel mileage, increased dramatically their power and output, and it's worked out pretty well.
There's more to this theory, but that's all we have time for today. We hope this video helps clarify some things. If you're interested in seeing more on this subject, or have further questions, let us know in the comments below. We will be doing a follow-up video, going more in depth over the re-geared vehicles soon. If you learned something new, or liked what you saw, tap that like button. And remember to subscribe to be notified about the next fun project in the Rear Wheel Performance Garage.